All right, thanks everyone for being here. This is a 90-minute tutorial. That's a long time, especially for someone as introverted as me. So I wanted to make it very casual. I want you guys to interact, ask questions. And I have a few activities scattered throughout. This is an unusual request, but I want you to take your cell phones out for this talk. And you are free to use them, look up different things, and also interact with a few online polls that I have scattered throughout the tutorial. All right, so net energy analysis is a subset of life cycle assessment, and I've been looking at it for a couple of years now, but I've benefited tremendously from my colleagues Dale, Adam Brandt, and Sally Benson at Clemson University, Stanford, and Stanford. So to start shifting our mind from thinking in terms of dollars and cents to kilograms and joules, I want you to participate in a little exercise. And this is a think, pair, share exercise. So I want you to think individually and then talk with whoever you're sitting next to about it. And then we'll share some ideas and then we'll take a poll. So on average, who do you think consumes more energy per day? A vegan driving a Ford F-150 Raptor, or a cyclist that eats nothing but meat? So go ahead, think about it for a minute or two, and then
talk about how far they drive. Yeah.
All right.
Otherwise, you give away the answer.
No, these are good things. These are good things. So an average American drives 10,000 miles a year. They both commute to their work with their vehicle. So go ahead, talk amongst yourselves. All right, so I'm hearing some pretty good ideas. Anybody have any general comments? Or does anybody want to say something specific about the paleo diet, what that might mean for energy use? Yeah, go ahead.
You have all of the energy inputs on the fertilizers and growing the grain, feeding the cattle, and all of the issues with the agriculture. You have to look at the water use also, for crops. And we haven't talked about what your vegan is eating, but some in California, the large users of water are not food crops. It's cotton and rice is a big one, for example. But I think you have to look at the energy budget on the water.
Absolutely. You're getting into points that are about 45 more minutes into the talk, but life cycle assessment is a very precarious sort of analysis with all sorts of caveats. Anybody want to say something more specific about what they think may be an energy difference between a vegan and a paleo dieter?
The energy intensity of the vehicle is very high. But again, the energy intensity of agriculture and all the life cycle inputs are high as well. You don't know the recyclability of the truck. You don't know where the fuel comes from. Fuel could come from Canada. They have hydraulic fracturing in Nebraska.
Absolutely, yeah. So it really depends on where you draw the boundaries in the analysis, and
you can't pick up hitchhikers on a truck.
You cannot pick up hitchhikers. Yeah, so. Sorry, I'm trying to get this poll going here. All right, so here's where I want you to use your cell phones, and we'll take a quick vote to see where the audience stands on this. So the way this works is you text one of these codes, this is what's in your message, to this number here. So this is who the text is being sent to. The text is being sent to 37607, and then in the message you select one of these two things. I've used this for over a year. They've never spammed me once, so don't worry about that. So go ahead and send a text and put your vote for the carnivorous cyclist or the vegan truck driver. "100% of the audience." Two votes. I'll give it about 20 more seconds. This is interesting. So it's a definite maybe. And we've heard compelling arguments for both sides. We've also heard some discussions that the analysis is very much dependent on boundaries and caveats, and so that may skew the final results. But all right, I think all right, apologies for whoever's just pressing send now, but we're going to move on. All right, so we had more votes, slightly more votes for the cyclists on a paleo diet, but all in all is certainly a definite maybe. So let's look at some of an analysis done by Chris McKay in his book, Sustainability Without the Hot Air. And so let's first look at transportation. Ford F-150 Raptor is the most tricked out Ford F-150, and it has an impressive fuel economy of 11 miles per gallon. In terms of kilometers per liter, this is 4.7. I mentioned each American drives about 10,000 miles per year, so that's 44 kilometers per day. We can arrange this to try to figure out how much energy is consumed per day by taking distance per day divided by distance per fuel, and then multiply that by the energy content contained in that fuel. Now, Chris McKay doesn't do energy conversions or things like that, and he uses a kind of funny unit. It's this kilowatt hours per day, and he uses this because this is a very human-sized unit. Now, a kilowatt is a power. It's an energy flow. You multiply that by a time hour, then you get energy. So kilowatt hour is actually an energy unit, even though it has this power sounding component to it. But the energy consumption, based on his analysis of a Ford F-150, is 94 kilowatt hours of energy per day. I assume the cyclist, sure, there's going to be some embodied energy with building the bike and manufacturing it, but I assume his daily consumption of energy associated with the transportation is zero. So now let's look at the diet difference between these two individuals. So Albert Bartlett, yeah, so I ignored the energy it took to make the bike, and I ignored the energy it took to make the Raptor. It probably took a lot more energy to make the Raptor. Yeah. So Albert Bartlett, a physicist, said modern agriculture is the use of land to convert petroleum into food. And so what he means by this is that the green revolution in farming, with the industrialization of farming and using fertilizers that derive from natural gas, we're converting a lot of fossil fuel energy into tilling the land and producing food. And so making food is energy intensive. We can start with thinking about a typical human being and what is their thermodynamic minimum just to stay alive. On an average basis, a human being needs 2,600 kilocalories per day. This is, if we convert from kilocalories to kilowatt hours, that's 3 kilowatt hours per day per person. That's just what it takes to run a metabolism. This is equivalent to a 100-watt light bulb being on for 24 hours. That's 3 kilowatt hours. Say you like dairy, say you have a cup of milk with dinner or a slice of cheese during happy hour, then you're going to add 1.5 kilowatt hours per day to that minimum. This is the energy required to keep a dairy cow alive, divided by how much milk it produces, obviously, per day. Say you have 2 eggs with breakfast, add another kilowatt hour per day to your daily dietary energy budget. You like meat? Add kilowatt hours per day. If you only like beef, add 16 kilowatt hours per day. The cold calculus, like the cold existential calculus with meat, is that the energy requirements, life cycle energy requirements with the meat is associated with how long the animal lives. So things like lamb and veal and chicken, goat are less energy intensive than a full size. What?
This is all for the US, these numbers.
These are actually for these are for the United Kingdom. That's where this analysis was conducted.
Probably less.
Yeah. That's a fair point. Energy consumed in fertilizing and farming is 2 kilowatt hours per day. That's the energy associated with the fertilizer and driving these vehicles around. And so if we look at the differences between a paleo dieter and a vegan, average person consumes 12 kilowatt hours per day. Vegan, at minimum, consumes 5 kilowatt hours per day. And a paleo dieter probably consumes somewhere around 20 kilowatt hours per day.
So for the paleo, are you still using the US numbers?
I don't know what you mean by that question. The average vehicle miles are US. These food numbers are probably for an average developed country diet. All right, so here are the results. Diet for the vegan Raptor driver is 5 kilowatt hours per day. The truck consumes 94 kilowatt hours per day for a total of 99 kilowatt hours per day. The cyclist base for 2,600 calories consumes 20 kilowatt hours per day, but this individual is probably consuming an additional 1,000 calories per day to ride their bike. And so they need to consume more food energy, add another 30. Conclusion is the vegan with the Raptor probably consumes on a daily average basis more energy than the paleo diet cyclist. But these numbers are actually kind of close, and it is still in the maybe range, especially given all the caveats associated with life cycle assessment. But if I were to place my chips, I would definitely put it on this truck as consuming more energy than the energy associated with food. Incidentally, you take one international flight a year, that adds, and you divide that through the 365 days, that's about 60 kilowatt hours per day. You take 2 international flights, and it's starting to wash over whatever car you drive. So you may be holier than thou and drive a very fuel efficient car, but be careful on how much you fly if you want to wear your Green Earth badge.
I think a lot of people really need to consider that.
Yeah. All right, so we looked at transportation, we looked at diet. I want you to share with your neighbor and think about how else do we consume energy. So go ahead, break it up. I can take a break. Anybody want to share some ideas? Yeah. Go ahead. Yeah, I just want to hear some other ways we use energy besides transportation and food. Yeah.
All right, shut up.
So my struggle with this one is, if I have money and I don't spend it on electricity or Hummers or cars or something, where does the money go? Most likely, my wife spends it on Amazon. Okay? So the carbon footprint of that money is more or less the same as what I would have spent on my electric bill or my car. And if I leave it in the bank, somebody else is going to spend it. Now it's a question of the velocity of money. How many times that money circulates through the economy? There's obviously the only way to be righteous about this is to be poor.
That's it. Tutorial over. No, go ahead.
Assuming that somebody took a shower in the morning and they heated up the water.
Hot water.
There's an enormous energy content in heating water, but there's enormous energy content in the preparation and transportation of the foods, whether the Amazon junk is get delivered by the drone.
So we've heard consumer goods, hot water, houses. How do houses use energy? Heating, cooling, electricity. Yeah. Making things bright and shiny, making things cold, making things hot.
So if you put PV on your house, What's the break-even point in terms of energy going into that?
We'll talk about that in about 50 minutes. Yeah. All right. So you guys hit on most all of these. There are a few indirect ways in which we consume energy as well. United States has by far and away the largest defense budget and has by far and away the largest defense energy expenditures. Shipping is a big deal. This obviously was a slide I used in a recent lecture, so you can visit friends in Seattle if you live in Bellingham, Washington. If you're from here, I suggest flying, which would count for here. All right, so the point of this slide is that we use energy throughout many different devices and technologies and habits throughout our life, and we benefit tremendously from all these things. But what about energy for energy? It also takes energy to make energy. And this is something we've known for probably since 2 or 3 ice ages ago when they thought hominids discovered fire. And it takes energy to collect firewood. Anybody who's ever been camping knows this, that as the night wears on, the distance to usable firewood increases and you have to spend more and more energy. And if your energy inputs, beer or wine, run out, then you go to bed. It also takes energy to get energy in advanced industrial energy systems as well. So here are massive dragline operators mining coal in the Powder River Basin in Wyoming. This Thunder Horse oil platform is, I believe, the biggest oil platform in the world, and it is the size of a city. Here are a bunch of cars at the beach for scale. Wind turbine blades are massive and made out of fancy materials, and solar panels are made out of molten silicon, which is a energy-intensive process. So this gets us to start thinking about what good is an energy system, what's good about it. Aristotle thought about what makes something good a long time ago in the classic Philosophy 101 translation of Aristotle's functional argument is a hammer, and a good hammer is a hammer that drives in nails straight and true. And so a good energy system might be an energy system that delivers more energy to society than it costs society. And so that is the basis for net energy analysis. It's concerned with how much energy it takes to deliver energy back to society. Some of the earliest thinking in this in a more formal sense, obviously humans have been thinking about net energy analysis on a daily basis for since their existence. But in a more formal sense, Charlie Hall back in 1972 was thinking about the migration of different species, birds, reptiles, and fish. And he was wondering why fish in local streams in the East Coast were going up and down depending on different times of the year, and also depending on the size of the fish. And I'm not talking about like salmon migration out to sea and then back to the stream. This is just within an individual stream. So at certain times of the year, the fish would swim several kilometers upstream and hang out there for a while, and then later on swim several kilometers downstream. And he looked at several different hypotheses for why they would do this, predation, that sort of thing. And he determined that it's because depending on the season, the fish can get much more energy in different locations. And they end up getting 25 times more energy in food than they spent in all that swimming back and forth, especially upstream. And so they can swim upstream, burn a bunch of calories doing that, but then they get repaid 25 times in food. And so the energy return for those fish is a factor of 25. Life in general is incredibly familiar with this. I mean, life is thermodynamically just a dissipative structure. We degrade energy gradients and create entropy. And to be able to continue to do that, we must acquire more energy than we consume. And so here's an Arctic fox spending energy, investing energy, trying to catch some energy. And if the fox gets more energy from the food than it spent trying to catch it, then it leads to great things in fox society like puppies. And if it spends more energy trying to catch the food than it gets from the food, then it leads to not so great things. All right, so I've talked a little bit about gathering firewood, but this is very familiar to energy use throughout human history. There's a really excellent book by Valkov Smil called Energy in Human History. But in general, early human societies were subject to energy return limitations. Hunters and gatherers they needed to maintain territories and capture more food calories than they expended going about that territory. There is an energy revolution. The first one was the use of agriculture. And so now we were able to grow even more calories than the effort expended in tilling those fields, because we begin to harvest solar energy in a sense. I'm going to switch gears for a moment here. I know that there are a lot of business people in the audience, and so I wanted to shift away from physics momentarily and think about financial analysis and how it's actually guiding this net energy analysis. So here are some very basic concepts in financial analysis that even I barely understand. So you have to invest money to make money. To be profitable, you need to make more money than you invest. Investments with high rates of return are better than investments with low rates of return. Investments that are profitable have a shorter break-even time, and they're easier to grow quickly. And so net energy analysis are applying these concepts to net energy analysis. And so in terms of net energy analysis, it takes energy to operate, decommission devices and systems needed to produce energy. For a device or system to be useful to the global energy system, not on some microscopic or local level, but globally, energy systems must produce more energy than they require for their manufacture and operation. And if this is the case, then they can bootstrap and grow, because this windmill will produce more energy than it took to build it, so you can use some of that excess energy, net energy, to build another windmill, and it can continue to take off. Some general insights from net energy analysis. A primary energy resource must provide more energy to society than it consumes. Energy resources that do not meet this criterion are either subsidized by other energy industries or are uneconomic. So what does that mean, subsidized by other energy industries? It wasn't last winter, but the winter before, in Nome, Alaska, there was a heating oil crisis. They got locked in by ice, and the delivery wasn't made before that ice reached there. And the United States employed a Russian icebreaker that was powered by 2 nuclear fission reactors. The amount of energy associated with obtaining that raw uranium, spinning it up, and then operating a fission reactor that's moving a massive boat at only, really slow speeds as it breaks through the ice to deliver some heating oil to a small village in northern Alaska. The energy return on energy invested for that, the amount of energy contained in that oil compared to the amount of energy in that boat, it's probably far smaller. So their energy return was not a factor of 25 like for the salmon. It was probably like a factor of 1 over 1,000. So that is not a way to run a global energy system, but in that specific instant, that energy was precious. And so there are instances where poor energy returns make a lot of sense because humans are important. What else? Here's some interesting insights that I think begin to start to unlock the power of net energy analysis. As resource quality declines, so does net energy availability. Yes?
I have a question about actual quality of the energy itself. It seems like the sort of net balance could be negative if you're turning sort of poor quality energy into higher quality usable energy. Yeah,
energy quality is certainly important, and that's something that we keep careful track of in some of these later analyses that we are doing. Some of the early analyses just called a joule, but as you will know, an electric joule or pure work joule is much more valuable and useless than some joules associated with a hot cup of coffee, for example. You can't run your computer on a hot cup of coffee. All right, so I know it's gotten a little lecture-y and not as fun, but we are getting through some of these basic concepts with net energy. So the Industrial Revolution was fueled by easily accessible and cheap, abundant fossil fuels. This allowed for a rapid and large payback, and it led to something called the upward growth spiral. So there's so much net energy and excess energy associated with mining coal and then later oil that we could build these industries very rapidly, mine more coal, explore more oil, and the available net energy to society continued to outpace the energy required to supply energy to society. And so societal energy use went exponential in the last 200 years. And historically, this energy sector has required very low energy investments, about 10% of the gross production. As we transition to renewables, this may increase, or as oil resources become further degraded, this fractional investment will likely increase. This is represented in a cartoon here. So here's the energy sector, and it's pumping energy into society, but it requires some energy to maintain the sector or to grow it. And as these ratios change, depending on energy resource quality, technologies available, it has, dramatic implications for societal economies. All right, this is the most boring slide, but I have to pay respect to some of the people that did net energy analysis before I did. Namely, Pete in 1992 defined net energy very academically and said net energy analysis is a determination of the amount of primary energy, so that alludes to energy quality, direct and indirect, that is dissipated in producing a good or service and delivering it to the market. The most common used metrics in net energy analysis are these energy return ratios. And so this looks at energy inputs, energy outputs. Sometimes this is time-based. They look at how these change over time. And that leads to another common energy return ratio, which is the energy payback time. It tells you how quickly a given energy investment will pay back its initial investment. So somebody asked about solar panels earlier. So this is a concern with paying back the energy required to manufacture a solar panel. So let's look at some of these returns. So here's an energy return ratio, compares the amount of energy produced by a system to that which it consumes. So add up all the energy outputs and divide it by all the energy inputs as they're added up. And then basic concept, if this number is greater than 1, then that's a successful energy industry in a global sense. So let's look at a single plant. We could call this a coal plant or a natural gas turbine, and that's where I'm drawing the boundaries at the plant. Has energy inputs in construction. And so this is energy flows, so inputs and outputs, and this is a time axis here. So at the beginning of the plant's life, there's a big energy sink in building the plant. While the plant's being operated, there's some energy associated with operating the plant, perhaps fueling it with coal or natural gas, and then it's generating energy to society. So that's energy production. And then at the end of life, there's energy associated with decommissioning and recycling the plant. And so the most common net energy analysis ratio found is this energy. Yes, a question.
I submit that your analysis isn't deep enough. Because in this whole discussion, we're assuming for a coal plant, for example, that the oxygen is free. Okay, and one of the outputs of the plant is CO2.
Sure.
Okay, and that's not reflected in this equation at all. And the problem is right now we're paying for the CO2, and we're going to continue to pay for this.
Yeah, so you're starting to get into external energy ratios or Earth system energy ratios. A complete analysis that includes all energy inputs, not just paid by society, but paid by planet Earth or the solar system or the entire universe, is always going to be less than 1. Well, yeah, so then we're starting to place an energy value on the oxygen and CO2. And that's certainly needed. These externalities need to be considered. In a simple net energy analysis. I'm not sure how that would be done. For the sake of comparing one energy system to another energy system, strictly based on societal energy costs as they are described today in economic terms by the United States and the entire planet, I'm just going to keep it right at the energy inputs that we actually put a price on. Yeah.
I'm curious why your gray bar is smaller than your yellow bar.
Because let's call this a wind turbine.
Okay, no fuel.
Yeah, this is just a cartoon. I said coal plant, but if we're actually going to look at the size of that block and take the integral over it and compare it to EG, then yes, it's going to be a wind turbine or some renewable source that doesn't require fuel. The basic concept is that the energy return on energy investment is all the energy generated by a plant divided by energy associated with construction, operations, and decommissioning. This is so-called life cycle stages. Another important energy metric is the energy payback time. So this is the time energy production technology takes to pay back all of its energy inputs. It has dimensions of time, usually years, and so this is all, it's kind of an inverse equation. It's all of the energy inputs divided by annual energy outputs. And so energy over time equals time, and that allows you to determine how many years it takes to pay the energy back. So in terms of that diagram, it'd be the energy inputs divided by the time derivative of energy generation. So looking at a coal plant here, and this is from White and Kolsinski. So this isn't actually looking at the fuel inputs, it's just looking at the operational costs of the plant. Here are the energy inputs for construction, operation, and decommissioning. And here's the energy generated over time. Here, the construction is 150 terajoules, operation is 83 petajoules, decommissioning is 20 terajoules. So we can first look at the energy return on energy invested for this plant. And so we put in the energy generated on the top and all the energy inputs on the bottom. So we can plug those numbers in. Does anybody catch a math error with this equation? Yeah, somebody said it, petajoules and terajoules. So that energy analysis, it's really important to pay attention to units. In general, you guys have already alluded to this with energy quality. That's an even deeper dive into what units mean. But in basic terms, I've confused petajoules and terajoules here. And so we can correct for that. And the EROI for this particular coal plant is 11/1. In terms of energy payback time, take the energy inputs and divide it by the energy generated per year, and it has an energy payback time of 3.5 years. So in general, non-renewable technologies have large operating and maintenance costs associated with the fuel cycle. Renewable technologies often have large upfront costs and minimal operational costs. The fossil fuel technologies are often described as pay-as-you-go, and the renewable technologies are pay-up-front. All right, that was a lot of lecture, so let's break it up a little bit. And just in terms of societal energy costs as determined by economists today, I want you to take a vote on which resource on average today has the highest energy return on energy invested. We can go back to that website, I hope.
On average over what time period?
Today. So I'm not talking about oil gushing out of the ground in the 30s. I'm talking about oil today, coal today, solar today. Solar post-2000, that's where the data is coming from. Wind post-2000. I'm missing class right now. Yeah, so again, this is who you send the message to, and this is the message. Yeah, so we're starting to get some maybes. We're starting to get some distribution in the results. Does anybody have an idea why solar PV might not have as many votes as some of the other technologies? It's just energy intensive to make. Yeah, it takes a lot of energy to melt those silicon wafers.
And not to throw a wet blanket on all of this, but building on a previous comment, the amount of water, 40% of U.S. water goes into electric power production. So there's huge energy.
Yeah, I thought it was even higher than that. I read recently it was like 45 or 47, yeah. No, yeah, absolutely. I'm only looking at energy here, but obviously this is a very connected world with many other things that matter.
Just cooling everything, cooling the house.
No, I hear your point loud and clear, and I subscribe to that point that we need to include many different things. Unfortunately, we're only really including financial analysis in most of the decision-making we make. Yeah. All right, so this looks pretty good. We have a good distribution, some high votes for oil, natural gas, and wind. One more for natural gas. So natural gas is actually an interesting thing because the energy associated with natural gas production's changed dramatically in the last 10 years with the advent of horizontal drilling and fracking, and so these numbers aren't reflected as well in this plot, which comes from previous work back in 1986. But hydro wasn't on that chart. But in general, wind, coal, and oil are very high, and solar is lower than wind by a fair bit. I have some updated numbers on solar, wind, and gas that I'll display later. Corn ethanol, depending on where it's grown, can sometimes be below 1. Yeah. Hydro performs so well because it has a huge upfront energetic cost to build the dam, but then it just runs for 100 years and continues to pay energy back. All right, so we've already explored a lot of this, but just in case we're not all on the same page, I want you to share with one another. Yeah, go ahead before we do this.
The analysis you did, like the example of coal plant for the energy electron investment. I think you mentioned that the coal is used to feed the plant is not considered in that motivation. Is that correct?
No, it wasn't.
This is like comparing a solar power plant to a coal-fired power plant based on ERRI. It doesn't make sense to me because on one hand you're feeding something, a bunch of coal pulled out of the ground, and on the other hand you're just sitting outside on a sunny day.
So the energy associated with pulling the coal out of the ground was included. The energy contained in the coal was not included. But there are certainly different, and this is, yes, certainly getting into some of the issues and problems associated with this. It really depends on where the boundaries are being drawn, and it's difficult to think of how to compare something like a coal-powered plant to a solar-powered plant. And so one metric that I think is useful is the net external energy ratio, which only looks at energy subsidies paid by society, energy paid by society to acquire these different resources. In the Athabascan tar sands, for example, there's a tremendous amount of energy that's used internally. They burn natural gas that's produced to heat the water to separate the sand from the bitumen. And so that isn't actually paid by society. Does it have environmental consequences? Absolutely. Does it produce CO2? Absolutely. But in terms of building an economy and society based on the energy drag associated with providing energy systems, then it may be a different metric. There's different metrics you can use for societal importance and environmental importance. They both need to be included. What else do people have problems with? Let's just get it all out. Yeah. Yeah.
For your oil, did you include the cost of maintaining the largest military in the world?
No, and that's an excellent point, and that's a question I've asked myself. And for the sake of not getting too political, yes, that is an important question. Yeah.
There's also a time value of energy, especially for electricity.
Right.
Cyclical time.
Right. No, yeah, and that's not included in these analyses so far. It gets very confusing using units like joules and kilograms, which can be measured to absolute precision, mixing those kinds of units with dollars, which are an abstract concept. Yeah.
And would those evaluations include the delivery system that is necessary? So if you have like local solar panels, but you have to have storage batteries, and there's energy required for
Right.
that process.
And that's up to whoever's conducting the research. Hopefully whoever's conducting the research is very clear about their boundaries. But yeah, it goes all the way back to who's driving the truck that moves the materials? How many Snicker bars did that individual eat? Did he stay at a hotel, and was that hotel built by individuals, and did they like come over on the Mayflower, and then like hopefully it begins to asymptote to zero, right? Because those energy expenditures 500 years ago are spread over all humanity at this point, so you divide by 7 billion, but it gets very tricky. Yeah.
I don't believe your wind numbers at all on that chart. That's old data.
Yeah, I don't believe them either.
Decommissioning numbers in there at all.
Yeah, I have some new values for you that I think you'll be pleased with. All right. So we obviously have some problems with net energy analysis. It's a very young science. It's terribly underfunded. Yeah. All right, so measuring total energy input is very difficult, requires knowledge of many different processes, technologies, the embodied energy associated with all those technologies and processes. There's a huge boundary problem. I think the only way around this is to just be very clear with whatever study you're conducting where the boundary is being drawn. And so then studies can be harmonized with one another. Metrics are often poorly defined. What is met by total outputs? Are we talking about electrical energy, heat, both? Energy types is another problem, source of confusion. Results are often overemphasized. So people just say, oh, this has an ERI of this, and this has an ERI of this. This must be better than that. But no, there's things like water, CO2, environmental degradation, human welfare, et cetera, that are all concerns as well. I saw someone with their hand up. Yes?
Do you use discount factor for calculating?
No, energy is conserved. I don't like that idea. But some people are definitely interested in that. But personally, I get really queasy when we talk about less energy in the future because there's always the same amount of energy. Exergy, you could talk about discounting exergy. All right, so these definitions are really simple, right? Just an equation with a few numbers in it. It's 4th grade mathematics, but the implementation and execution of net energy analysis is very complicated, as we're beginning to discover. It's easy to talk about. It's difficult to actually collect the data and perform the math. Energy products are produced in very complex pathways. I mean, we're talking about truckers and Snicker bars. Indirect energy consumption can occur in many different industries. How much energy does it take to make a PhD to seismically analyze an oil reservoir? Do we have to include all the energy it took to train that geophysicist?
Speaking about this energy,
yeah. And so Adam Brandt here at Stanford, McDale at Clemson, and myself are trying to standardize some of these methodologies, but right now it is a bit of a hornet's nest. We have something like 20 different operational definitions in one paper. Matt Pello, a postdoc at GCEP, is looking at energy analysis associated with fuel cells, which are really complicated because is it a energy generation technology? Is it a storage technology? Is it a consuming technology? Yeah, so it's a complex thing, but we are working on it, and I think it has a lot of promise and can really add to policy debate in the future when we're looking at carbon costs, water costs, energy costs, as well as financial costs. We're going to take a short break, and then we're going to look at 3 examples. Athabascan tar sands from Adam Brandt, the PV industry from Mick Dale, and energy storage from my own work. And then I want to share some insights from a paper that Mick wrote this summer on 5 ways net energy analysis can benefit society. So just a short break if you need it, and I'm happy to field questions. All right, so I'm going to go through 3 examples: the tar sands, the PV industry, and energy storage. So in this first example, it was conducted by Adam Brandt, and I believe his first name is Jacob Englander, here at Stanford. And they looked at the energy inputs and energy outputs of the Athabascan tar sands from 1970 to 2010. They considered 2 main different boundary conditions. They looked at the net energy ratio, so energy outputs over energy inputs, and then at external energy ratio, so energy outputs over societal energy inputs. This one has much more environmental ramifications because it's considering all the energy being consumed on site, natural gas being burned, oil being consumed from the tar sand resource itself. This external energy ratio has more economic repercussions or significance because it's asking how much energy was actually shipped to Alberta to produce these resources. Any guess which one is going to be bigger? Is all of the energy inputs going to be bigger or smaller than the societal energy inputs? So if all the energy inputs are clearly going to be bigger because this is energy on site, which means this denominator is going to be bigger, which means this ratio should be smaller. All right, so here is their time series data of the net energy ratio. So this is the environmentally important one. Wait, let me make sure I'm getting that right. Yeah. This is the environmentally important one. And so you can see some improvement with time at 2 different sites. This POU stands for point of use. So this is where the resource is actually being used at a oil refinery or oil power plant, not at the mine mouth per se. But the EROI for these tar sands at point of use are about 3.25. If we look at their EROI with respect to cost to society, the net external energy ratio, then the EROI is about 10. And that's because it's consuming some energy on site. They did see slight improvements in this one as technologies and mining practices have improved. In the long run, these ERIs are expected to go down as the resource becomes depleted and less accessible. The low-hanging fruit gets picked. And it's getting really low with oil price depreciation happening in the last 2 weeks. Here's the PV industry. So this analysis was done by Mick Dale. He's really interested in not just static EROI values, but how EROI changes with time or more dynamic things. When industries are in a subsidy period or when they're in a producing period and how that transition happens. So these are all his words, and he states that amortized metrics such as cumulative energy demand, so that's the total energy spent in a particular technology pathway, may disguise the cost of rapid scale-up or the cost of transitioning from one energy source to another. The timing of material and energy imports is important. So this is that reflecting that pay-as-you-go model with fossil fuels versus the pay-up-front model with renewable resources. And yeah, so to state that again, renewables require this upfront payment. All the energy and financial capital is paid at once, and then it pays its dividends over time, whereas fossil fuels, in an energetic sense, require less upfront energy costs, but then they require continued energy payments during their operation. Yes.
I noticed you have the energy commission very much index. For example, the fuel costs can go up or down. Did you sort of ignore that?
In the energy analysis, yeah, because the energy price, the amount of energy is thermodynamically tied to whatever you're building and the technologies in which you're building them. Water doesn't care how much it costs to split water. It's always going to take whatever that is, 1.37 electron volts.
But you mentioned at the bottom, the fossil fuels have larger operating costs. That's very broad talking about.
These are mixed words. I'm assuming he's talking about energy, larger operating energy costs. You have to forgive Mick and I, we're physicists, so when we talk about costs, we're usually talking about joules. But here I'm trying to separate this distinction, this problem with cost. So here is financial costs. This is a pie graph put into a bar, adds up to 100. Here are financial costs associated with PV manufacturing versus energy costs. And so the energy costs with giving some people Snicker bars and having them hammer stuff onto the roof are much lower than the financial costs associated with paying people to do that. That's one clear difference. Yes?
Yeah, just to clarify this, I mean, when you talk financial costs and somebody says, oh, I'm buying a solar panel and it costs so many dollars, isn't the energy that made the solar panel somehow reflected in the cost of the solar panel? People can't say, oh, I'll sell you the panel for less than the cost of production. I mean, unless you're in China and you're doing this because you want to encourage the volume or something. But I don't understand. Aren't these somehow embodied one inside the other? The financial cost has to incorporate the embodied energy.
But a joule is not a joule in a financial sense. So, I mean, where do we refine aluminum? We refine aluminum next to geothermal and hydroelectric sites that are cranking out kilowatt hours of energy all night long.
But when someone buys the bauxite and reduces it by jamming electrodes into it and hooking it up to the dam and sells you the aluminum, the price they sell you the aluminum has to somehow reflect.
It certainly reflects the energy cost. But energy costs aren't equal in time and space. And I think this chart really reflects that. Yeah.
The other thing relates to this is
financial costs of energy are not equal in time and space. Energy costs are equal in time and space.
It's not ultimate uses of energy. It's a fungible commodity, just like money is. And as you peel back additional layers, particularly for something as huge as the energy market, which can swing the dynamics of energy and it can move into nonlinear parts of the curve in terms of what it takes to extract that incoming energy or those incoming raw materials. Somehow you have to peel that back and you get back to what you said at the beginning, which is, the second law of thermodynamics is ultimately you're going to have to number less than one on these energy ROIs.
Yeah.
So the way the economy works typically is things like shadow pricing and proxies like that to basically put the barrier around the system that they're trying to measure and get an equal playing field for everything else behind that. And somehow you have to make a decision where you're going to draw the line here. You're just going to end up with a number always that's less than one, and all you've done is proving the second law of thermodynamics.
Yeah, so usually we draw the line at societal energy costs. We don't count how much energy came from the sun that hits the solar panel. We only cost the energy cost to build the solar panel.
But I think in going back to raw materials, as you push deeper into raw materials, you're quickly getting to the point where you're ending up. I think the analysis runs the risk of ending up with meaningless results, and that's why there needs to be some kind of equivalent to shadow pricing in economics, fairly close into what it is you're trying to measure.
I agree with you. I think boundary conditions are a tremendous issue and need to be carefully explored. I think we have a lot to learn from the economists. I think they have a little to learn from us, too. So here, energy flows. So this is what Mick's getting at. He's not looking at the total EROI at the end of the day or 30 years down the road. He's concerned with dynamic EROI over time. And so he drew up this nice cartoon to show some of this. So this is the industry flows associated with growing industry. This is just cartoon. These aren't actual values yet. So your energy inputs on year one, some energy is paid by society to build a solar panel. Year two, an additional energy unit is paid. This first one is now starting to produce electricity. Year 3, society decides to build 2 more solar panels. These first 3 here are now producing electricity. And so on. And in this specific case, the industry is operating in a deficit. Each year, society is paying more energy out than it's getting back from those solar panels on a yearly basis.
Just to clarify this, let's stop right there making any more investments and just use what we have. Wouldn't we get net return in a few time units we had to take?
Yep, that's exactly right. So at this point, society has decided to not invest any more energy, or to invest decreasing amounts of energy on a time derivative sense into the solar panel industry. But these ones that have been built all along are now generating electricity and will continue to do so. At some point, the amount of energy produced is going to equal the energy subsidy, and that's going to be this break-even year. And after that, we'll continue to pay energy back. The question with respect to the PV market is has it reached that break-even year? Or is society paying an energy deficit to provide energy to build the PV panels?
And a related issue is that if you increase your PV penetration or any renewable beyond about 10%, you have to start worrying about issues of how you're going to integrate it.
Yep, and you're going to increase your energy cost by building peaker plants and storage. We'll get to that. So here's the net energy yield growth and energy costs associated with the PV industry. This plot shows the growth rate of the industry on the y-axis, percent per year, and this x-axis shows the energy payback time in years. Energy payback time is linearly proportional with the energy cost per kilowatt hour peak. And so to begin to plot technologies on this graph here, we need to have 3 different numbers. We need to know what the industry growth rate is, percent over time. We need to know the capacity factor of these PV systems, because the energy cost is kilowatt hours of energy paid per watt peak, but they don't always deliver at watt peak. They deliver at some capacity factor of watt peak. And we need to know the energy cost. So the PV industry is growing rapidly. Average growth between 2000 and 2010 was 40% per year. Most of that is crystalline silicon. Global capacity factors, the median is about 11.5. That's because of the tremendous PV penetration in northern locations, mainly Germany. And the third number we need is the energetic cost for PV. Mick conducted a meta-analysis. He consulted several different studies, and he found the energy in kilowatt hours per watt peak is technology dependent, and is around between 3 and 5 or so for crystalline silicon. Energy costs are decreasing with time as people get better and better at making solar panels. This is called technological learning, and this proves true in most all industries, including the PV industry, and it's reducing the energetic cost of PV technologies. So because of that reduced costs over time, this again is that plot with growth rate and energy payback time, which is proportional to energetic cost here. So this is 2012, so I don't know what this is. This is 2000 or something for one particular technology, CAD-TEL. So in the year 2000, the growth rate for CAD-TEL was 10 or so, and the energy cost was 5 kilowatt hours per watt peak. Year later, energy costs reduced, but growth rate increased. Trend continued. The growth rate became so excessive in 2010 that there was actually an energy deficit. That's because society was building so many of these panels, they weren't paying back the energy yet. But as costs continued to go down, energetic costs and growth rates slightly reduced, CAD-TEL is now in the energy surplus region. It's delivering more energy to society today than society paid for it, and it will continue to do that over time, assuming these growth rates stay similar, because the ones that were built yesteryear will now be producing energy. Here are the net energy trajectories for all the PV technologies. Most technologies are at break even or will break even shortly. So in conclusion, the PV industry is a net energy provider and will continue to grow as a net energy provider to society as time continues on. Yeah, Mark.
So one of the things about this is like this almost this connotation that a brief energy payback time is a good thing, and yet I would think if you invented the greatest energy technology today, although not like an infinitely great one, but like a practically but really great one, we would spend a huge amount of energy, transforming the world's energy system.
Yeah, that's what we're doing with fusion. We've paid so much energy into that. But it's an excellent point. And I think both numbers are important. The EROI, the static one, over the course of the energy technology or resource, and this dynamic one is important in terms of. It starts getting kind of philosophical. If society has more net energy, it can do things besides the energy industry. We can, have arts and philosophy and things like that. But, and so this is looking at, I think Mick's emphasis here is the solar industry impinging on energy availability today? Clearly it will deliver more energy down the road because it has an EROI above 1. But your point is absolutely true. If there's a technology with an exceptional EROI, then we should pursue it for the sake of, our children or something. All right, so that was the PV industry, but someone made the point that as the penetration of renewables increases, it will provide complications on the power grid because these resources are weather dependent, they're intermittent. This is a picture of California independent service operator operations. This is a military secure building. These people have a very serious job because they have to continually and constantly balance power supply with power demand. Otherwise, factories and computers break if we deviate from that 60 hertz, or the power grid just goes down.
These guys export power and re-import it, make more money.
I don't know. I think these guys are more just, they want to keep the grid right at 60 hertz. It's beyond the scope of this talk. So here are 30 days of wind generation in blue, solar insolation in gold, and power demand in red, superimposed on each other. This is a pretty common plot nowadays, but it just shows that power supply from renewable resources does not correlate with power demand. And so we necessarily, as the penetration of renewable resources increases, we need to develop more flexible technologies on the power grid. And we can do this in several different ways. We can improve forecasting, determine when the sun is going to shine and when the wind is going to blow, and deploy resources as needed before the problem becomes apparent. We can increase aggregation, begin to share electrical resources with neighboring communities. We can deploy flexible dispatchable generation. So modern aeroderivative natural gas plants operate just like an airplane engine. Airplane turbine, they can speed up, they can slow down, so they can adjust the amount of power they're delivering to the grid as needed. Or we could deploy energy storage, which acts as flexibility in two ways. It can be an energy sink, and it can be a source of electrical energy for the power grid. So in my net energy analysis, I explored 3 different flexible generation pathways. Stored renewables, so electricity generated from a windmill at night, for example, charges storage, and then when it's needed the next day, it can be dispatched to the power grid. Another pathway is grid storage, so here electrons are taken from the grid, put into energy storage, and then dispatched back to the power grid.
To clarify, the electrons that went on the grid and grid storage came from where? They had to come from some source.
I assume grid average source, so, and that's going to be regionally specific, and in this analysis I looked at US average grid. And then responsive gas generation takes natural gas from the gas network and runs it through a turbine generating electricity. So the question I was concerned with, how do these 3 different pathways compare to one another on an energetic and a carbon intensity basis? Well, But here's a little formative assessment to see what you guys think about it before I go into the analysis. No internet polls anymore, we're running out of time. Should we store wind? Raise your hands for storing wind, or let's do thumbs up, thumbs down. Thumbs up for storing wind, or thumbs down for curtailing it. Most people think we should store it. Few thumbs down. Obviously, it's going to depend on technology, all sorts of other things. What about storing solar or curtailing it? Should we store it or curtail it? Store solar. Should we store wind energy, or should we use natural gas peaker plants? Both. So you're saying the world's a complex place and we can't just do one or another, and I've created a false dichotomy? Good. Let's just get into the analysis. All right, so the methodology, I mainly focused on developing a theoretical framework to perform this analysis because it didn't exist yet, and also because the data is poor. The CO2 data is quite good. The energy data is in want. So I looked at energy storage and energy generation life cycle assessment studies, both in energy and carbon. As best I could, I tried to truncate all the analysis to cradle to gate. So this boundary is drawn as soon as electricity leaves the device. I don't care what's happening once it enters back to the power grid. And in terms of batteries, cradle to gate means as soon as the battery was manufactured at a factory. I'm not considering the energy it took to be transported somewhere. And so this is the gate in which whatever I'm looking at is being handed from the producer to the user. This is getting a little weedy. Okay. Grid scale technologies, there's a lot that were talked about in the previous technical session. Technology is improving rapidly. I have no doubt that we'll see some really impressive stuff 10 years from now. I only looked at technologies that are available today, and first and foremost, to be used on the grid, it needs to be safe. People don't like it when electrical systems kill them. So they need to be safe. Next, they need to be cheap. They need to be economically viable, and to be economically viable, they usually are made from abundant materials, have high cycle life, and they don't waste a lot of energy, so they have high round-trip efficiency. None of these technologies satisfy all of these criteria, except for the safe one, but most of these technologies satisfy a few of these. And so traditional lead-acid batteries, like you might find in a car, sodium-sulfur batteries, flow batteries, compressed air energy storage, and pumped hydroelectric are geologic storage technologies. So one of the first simple analyses that Sally Benson and I did was we tried to find an equivalent ratio to the energy returned on energy invested that encapsulated a lot of these important storage parameters, things like cycle life, depth of discharge, and efficiency. And so this is the energy stored on energy invested. It's the total amount of energy stored by a storage technology over its entire lifetime divided by the cradle to gate energetic costs. And as you can see, there's a big difference between geologic storage technologies and electrochemical storage technologies. This is primarily due to two reasons. The cradle to gate energetic costs are lower for these because they're either a hole in the ground or a hole in a salt dome. No complex materials or chemistries involved with that. The second reason is they have really high cycle life values. So a hole in the ground or a hole in the salt dome lasts for 25,000 cycles. Whereas electrochemical storage technologies suffer from much shorter cycle lives, between about 200 and 1,000, or 10,000, depending on the technology. I see a lot of room for improvement with cycle life counts for electrochemical storage technology. So I'm not saying that we should totally ditch them. I'm just saying today, as it stands, pumped hydro is a much better option from an energetic perspective. Yeah?
Remember the number of the case technologies that were used actually use natural gas-fired generator. We work in a single cycle rather than combined cycle.
Yeah.
Whereas energy efficiency actually is pretty awful.
Yeah, so I looked at the AC-AC efficiency, electrons in versus electrons out. In this efficiency, I did not consider the energy costs of the gas itself. So there's actually two efficiency values. There's actually like 4 efficiency values for case measurements. It's a tricky beast. That being said, natural gas is consumed with case operation, and so the CO2 emissions with it, even though it has great energetic performance, it has very high CO2 emissions associated with its operations. Natural gas needs to be burned as the air exits the cavern because of the ideal gas law. Pressure goes down, so temperature goes down, and ice on a turbine blade is a horrible thing. Yes, lead acid has high CO2 costs associated with it because they don't last very long. The traditional lead acid batteries don't last long, and so they need to be replaced often. And even taking into account lead recycling, the energy costs and CO2 associated with it is high. And this was all studies conducted over in Argonne National Laboratories. An important thing about energy storage is they aren't perfectly efficient. Energy is wasted, and so that will increase the amount of carbon associated with the energy resource that charged the storage in the first place. So it's something I call a source carbon multiplier, which is 1 over the efficiency of the technology. So to deliver 1 megawatt hour from a lead acid battery, you need to put 1.11 megawatt hours into it because it's not perfectly efficient. That's going to increase the carbon intensity of whatever charged that battery.
How can the compressed air energy storage be greater than 1?
Because this is the AC efficiency. I put in 100 electrons. I actually got 136 out because the natural gas combustion spun that turbine even faster than it normally would have from the air. Basically.
Carbon burden from the consumption of the methane and the natural gas in your carbon multiplier? Because you're burning methane.
Yeah, so I do that. I'll show you the equations shortly. Here are updated EROI values for the resources considered here. I only looked at post-2000 values, so that other study was 1986. This is post-2000. There is not a lot of data for natural gas yet because it's so tied up with oil. But from those resources, I determined that natural gas has an EROI of about 14, PV has an EROI of about 12, and wind has an EROI of 86. So both PV and wind have increased significantly compared to that older plot due to technological learning and better data. Carbon life cycle costs associated with these resource technologies, so PV, wind, and gas, were acquired from the National Renewable Energy Laboratory, LCA harmonization studies. These are excellent resources and very carefully done. So for PV, 39 to 49 kilograms of CO2 are emitted over a life cycle basis per megawatt hour. For wind, 3 to 45 kilograms of CO2 are emitted per megawatt hour generated. And for gas, 420 to 670 kilograms of CO2 are emitted per megawatt hour generated. So we have the energy data, we have the carbon data. We can start combining these with some math. So to get the energy return on energy invested for one of these flexible generation pathways, this one in particular, I have to look at the energy return. So solar panel puts phi units of energy into storage, only eta phi come out because storage isn't perfectly efficient. So the energy return to the power grid is eta phi. The energy costs are the energy intensity of the resource plus the energy intensity of the storage technology. I don't have time to explore what those mean. We can talk about it later. So energy output over energy inputs is this. And then the greenhouse gases associated with this are the per cycle greenhouse gases associated with operating the storage. And so this, with building the storage, this is capital costs, operational costs. So this is going to be really huge for compressed air energy storage associated with storage. And then the greenhouse gases associated with the resource divided by the efficiency of the storage or multiplied by that carbon multiple. All right, so this plots these different flexible generation pathways on a EROI basis on the x-axis, bigger is better, and a carbon efficiency basis, which is the inverse of carbon intensity. So this is how many kilowatt hours are generated per kilogram of CO2 chucked into the atmosphere. I plotted it in this funny way because I wanted bigger numbers to be better, and I wanted to look at 4 different quadrants that the plot can be divided into. I quartered the plot by looking at the US power grid average. And so the US power grid average has an EROI of about 18. This is looking at all the different resources that go into that grid supply mix. And then the carbon efficiency of the power grid. So pathways that have better carbon efficiency and higher EROI than the US power grid average we should employ today. Pathways that perform worse than the US power grid average we should think carefully about, probably avoid. In this region, we're trading low carbon for less energy. I think that's a that's a good trade. Carbon is, I think, I'm personally more concerned with carbon than I am with energy use. And this region here, we're trading energy efficiency for high carbon emissions. So something like a coal power plant would be down here. Energy efficient, but less carbon efficiency than the power grid average. All right, so let's look at the natural gas technologies. The air bars aren't showing up on the screen, they're on my computer. But so here's a natural gas combustion turbine, slightly less efficient than power grid average. The new aeroderivative natural gas turbines are comparable with US power grid average. Here's natural gas combined cycle. It's not as flexible, but less carbon than the US power grid average. Natural gas combined cycle with CCS is not a flexible technology. There's thought now that if we could operate it in a swing mode where we capture carbon at an efficiency cost and then let it go at an efficiency gain, that it could be operated in a swing fashion. Anyways, we're really trading low carbon for slightly less energy. This is what happens when we store electrons for the power grid. So technologies in black take electrons from the power grid and then put it back onto the power grid. Pumped hydro performs better than a natural gas combustion turbine, but all other technologies have an energy penalty and a carbon penalty when compared to the US power grid average. Unfortunately, lead-acid batteries have the lowest financial capital costs of any technology, so they're being used in places like Germany and California, but it is the absolute worst idea based on a carbon and energetic basis. This is what happens when we store solar electrons. Here's PV direct to the power grid. This is what happens if we curtail PV at 10%. So if we have too much PV in the late afternoon and we just let it go, that might not be a bad idea, especially compared to trying to store it with lead-acid batteries. Storing PV with lithium-ion, pumped hydro, vanadium redox, these are good ideas, low-carbon pathways. Wind looks like a dream. Wind direct to the grid is way up here. It's a factor of 50 less carbon intensive than the power grid, and it's about a factor of 5 more energetically efficient. Even curtailing wind at 30%, throwing away 30% of our wind, performs as well as storing it with a pumped hydro storage system. Wind plus lithium ion is still a super attractive flexible grid technology. It performs way better than US power grid average and totally trounces a natural gas peaker plant. Wind with a lead acid battery is way over here. This is just ridiculous. I don't know what it'd be like maybe driving a Tesla with 4 flat tires. Yeah.
What duration of storage?
This is bulk storage, so 12 hours to 24 hours, or 6 to 24 hours. These are all bulk. This is not frequency regulation. This is shifting electron use from midday to afternoon or from night to day.
Did you look at cost?
No. I only have 5 minutes left, so I want to pour through some of this last paper that Mick, Adam, and Sally and I wrote, trying to promote the idea of net energy analysis for a societal use. So this paper came out in Nature Climate Change this summer, and we titled it A Better Currency for Investing in a Sustainable Energy Future. And we had five points why policy analysts should look at this. It provides a second way to value energy resources beyond just the financial. That last example shows that clearly. Lead acid batteries are cheap, but they're not good from a carbon and energy perspective. net energy fuels the economy. The more net energy available, the less that's being consumed by the energy sector itself, the more energy is available for puppies in Fox society. Third point, we can assess environmental impacts. So Adam's done careful work looking at net energy ratios and net external ratios. One is more societal implications, one has more environmental implications. If we look at pure net energy ratios, especially with fossil fuel intense resources, then we can use that as a proxy for environmental change. Fourth point, early technological appraisal. I go to a lot of storage conferences. They often say that we are storage technology agnostic. I'm not. I'm storage technology prejudiced in the extreme. They do not compete with one another on an energy and carbon basis, and we need to improve electrochemical storage technologies by improving their cycle life foremost and their efficiency second. And Zhen Bao and Yishui are making great strides towards this end. Finally, managing the energy transition. We don't have to go about it in this financial or organic fashion that we've done throughout the last 200, 300 years. We can perform analysis now before we make decisions and hopefully guide some of these decisions. Mick Dale made a nice analogy for net energy analysis. He said it's another important indicator on how society could be conducted. And so a plane has both an altimeter and a speedometer. These are the two most important things. And if we're just doing financial analysis, it's just flying a plane without the speedometer, for example. So as many indicators as we can get, that's the better. Maybe we can have one for water, CO2, selenium, mercury. This is why this is important. So I thank you for your time. I'm happy to field questions. Mick Dale knows a lot of this. So does Adam Brandt. So Sally does as well, but she probably gets too many emails, so I didn't put hers up here. All right, thank you for your time. You guys got any questions about this?
I have one question. Why is hydro so bad? I mean, below average?
Pumped hydro down here?
Yeah. What's the price? How did it work?
This is not hydroelectric. Hydroelectric would be up here. This is pumped hydro. This is taking grid electrons and pushing water uphill. Yeah.
I didn't hear you mention hydrogen. If you did, I apologize. How bad is hydrogen as far as moving backwards on energy return on investment and all that other stuff?
It's both good and bad. It really depends on the electrolyzer, the fuel cell, and the hydrogen storage technology. And this is work that Matt Pello, I don't know if he's still around, is exploring, and he's about to submit that paper, but he's really looking at all those different parameters, and he's comparing it to energy storage technologies as well, and putting them in energy systems. So what we're really finding out, it really depends on the whole system. Where the energy, what the energy resource is it wind, solar, grid, whatever, what the storage technology is, and how and when it's used. Yeah. Yes.
In other places, you refer to the fossil fuels, but you don't refer to nuclear. It would seem to be you want to have that analysis in here too.
I do want that analysis in here. The latest analyses I've seen for nuclear are in the 70s and 80s. They have an EROI between about 10 and 20. I think it's an important thing to look at, and I'm writing a proposal with Mick Dale to perform some more analyses on nuclear right now. Yeah.
You talked a little bit, just almost in passing, about net energy analysis being primarily a proxy for carbon analysis.
Yeah, I want to be careful with that. I would say it is if we're talking about a specific energy technology that's largely fossil fuel based. So if one oil field has a much better EROI than another oil field, then I would put money on saying that the better EROI oil field has a lower carbon intensity than the low EROI oil field. I would say light sweet Saudi crude has a lower carbon intensity for producing that resource than the Athabascan tar sands, for example.
And is the point of net energy analysis to inform policy and sort of primarily? And is the policy that, and its justification for that because of all of the subsidies for energy, which is motivated by environmental concerns and primarily climate change? Is that the whole point of net energy analysis?
I think that's one very promising selling point of net energy analysis. I think it can be another tool to guide policy decisions. I think it's really interesting to think how much energy is required to fuel different energy resources in society. I think it can, definitely help with decision making. And just because of the second law of thermodynamics, anytime energy is converted from one form to another, there will be environmental change. That's what the laws of nature dictate. So if we're spending more energy to convert energy into forms that are usable for society on one resource than another, then by proxy, that resource will have more environmental change. Maybe some of that environmental change will just dissipate into outer space as heat, and others will produce CO2, but I think it's an important thing to include in the analysis. I don't know. We're just starting.
But if you strip away the proxy function for carbon, and just take that away and just totally stay within the energy analysis.
That's probably a safer thing to do. It would have avoided this embarrassing.
Just sort of take care of itself. I mean, not very good technologies not go anywhere anyway.
Yeah, but we can keep ourselves from making poor decisions like planting the entire Northwest with corn and making gasoline out of it.
Oh, we can avoid that.
Yeah. Or putting lead acid batteries all over the power grid. Yeah.
Isn't the high CO2 content of steel and cement that brings nuclear down to the 10
I believe so. I haven't looked into it terribly, but I think there's a lot of energy associated with refining the uranium too, the centrifuges that concentrate U-235 or whatever from the yellow cake. Oh, I'm done, apparently. I'm happy to talk with anybody later.